Hello, students. In today's lecture, we are going to learn about thermodynamics, NCRT section 11.6 and 11.7. This is disclaimer, learning objectives. By the end of this lecture, you will able to understand the fundamental concepts of specific heat capacity, including both specific and molar heat capacities and their mathematical expressions. All right. In today's lecture, we will cover first 11.6 specific heat capacity, then 11.7 thermodynamic state variables and equation of state. So let's start. Specific heat capacity. So before starting the specific heat capacity, here question arises, what is heat capacity? All right. So imagine you have a two container of water, one small cup and one big bucket. All right. If you heat both with the same flame for the same time, in that case the cup temperature will rise faster than buckets. Yes or no? So what is the reason? Because the bucket needs more heat to raise its temperature. It has a larger heat capacity. So basically, heat capacity of a substance is defined as the amount of heat required to raise its temperature by 1 unit, or we can say by 1 degree Celsius or 1 Kelvin. It tells us how much heat the entire object needs to get warmer by 1 degree. The mathematical expression of specific of heat capacity is capital S is equal to delta Q divided by delta T. All right. So here, uh, delta Q is the heat supplied measured in joules, whereas delta T change in temperature measured in Kelvin or degree Celsius. All right. And S is the heat cap. Heat capacity has two main types. First, specific heat capacity. Second, molar heat capacity. And we will learn both one by one. So first is specific heat capacity. So as name suggests, specific. So here we talk about any specific thing. So specific heat capacity of a substance is the heat required per unit mass to raise the temperature by 1 unit or 1 Kelvin or 1 degree Celsius. So here the specific term is used for unit mass. So for raise the temperature, one raise the temperature of 1 unit mass by 1 degree Celsius. The required heat is specific heat capacity. Mathematically, the expression is capital S divided by M, where we know capital S is the heat capacity and M is the mass, unit mass. And we know the value of capital S, that is heat capacity. So delta Q divided by delta T. So specific heat capacity becomes delta Q divided by M into delta T. SI unit joule per kg per Kelvin, because here the in Denominator, there is a heat supplied, the unit is joule, and in numerator, mass, a unit is kg, so it will be per kg, and for temperature, per Kelvin. Specific heat capacity depends on two things. First, nature of the substance, and second, its temperature. It means the nature of the substance and the temperature is changed, so the value of the specific heat capacity will also change. All right. So look at here, NCERT equation 11.5. These are two important terms. First, M mass, uh, and second, delta. So from this expression, it is clear that the specific heat capacity, it also depends on M and delta T. Example: specific heat capacity of water is approximately 4.184 joule per gram per degree Celsius or per Kelvin. So the meaning of this term, 4.184 joule per gram per degree Celsius, is uh, it takes 4.184 joule of energy to raise the temperature of 1 gram of water by 1 degree Celsius. So the required heat, listen carefully, the required heat to raise the 1 gram of water by 1 degree Celsius is 4.8 4.184 4.184 is for joule. So this is the specific heat capacity of water. All right. Second is molar specific heat capacity. So here, uh, the term molar means mole, number of mole. So molar heat capacity means the amount of heat required per unit mole to raise the temperature by 1 unit or 1 degree Celsius or 1 Kelvin. So molar heat capacity, C is equal to capital S divided by mu per unit mole. So S by mu. Or we know the value of S, that is delta Q divided by delta T. So put the value, you will be get C is equal to delta Q divided by mu into delta T. Alright. So this is the mathematical expression of the molar specific heat capacity, where mu is the number of moles. If we talk about the SI unit of specific heat capacity, so it is joule per mole per Kelvin. Why joule per mole per Kelvin? Because look at here, NCERT equation 11.6. Here delta Q, heat supplied. For heat, the unit is joule, and the terms that is having in denominator numerator, mole and temperature. For mole, number of moles, for mole, and for temperature, Kelvin. So it is having in denominator. So we can say joule per mole per Kelvin. Example: molar heat capacity of water is approximately 75.3 joule per mole per Kelvin. It means it takes 75.3 joules of energy to raise the temperature of 1 mole of water by 1 Kelvin. In other words, we can say the heat required, or we can say the energy required to raise the temperature of 1 mole of water by 1 Kelvin is the 75.3 joules of energy. And this 75.3 joules is the molar specific heat capacity of water. All right. And it depends on nature of the material. Molar heat capacity depends on nature of the material. Specific heat at constant volume. So here, uh, volume is kept constant. So let's see the definition. amount of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius when the volume is kept constant. So here the important point is this: the volume is constant. So volume is held constant, so we can say delta V is equal to 0. So no volume change, no volume change. In that case, no work done, because work done is depends on volume, or we can say the formula PdV, pressure into volume, change in volume. So here volume is 0, so we can say no work done. So W is equal to P into delta V, change in volume. So change in volume is 0, so no work done is also. From this relation, it is clear that work done depends on volume. Volume 0, work done 0. All right. First law of thermodynamics, that is delta Q, heat supplied to a system, is equal to internal energy of that system plus work. So since we know no work done, it means W equal to 0. So we get, when we putting the W in the expression of the first law of thermodynamics, it will be delta Q is equal to delta U. It means the heat supplied to a system is converted into its internal energy and using to raise the internal energy of that system. All right. And we know CV is equal to delta U divided by delta T, because internal energy depends on temperature. All right. So if we talk about the internal energy, so it become delta U is equal to NCV dt, NCV delta T, where, or we can say N mu CV delta T, where mu is the number of moles. All right. So this is the specific heat at constant volume, delta U divided by delta T. So this is important relation. So remember this. Specific heat at constant pressure. So amount of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius or 1 Kelvin when pressure is kept constant. So uh, in this term, the pressure is held constant. It means delta P, change in pressure, is equal to 0. So if the pressure is 0, so work done is due to the volume change. That is W equal to pressure into delta V. So using the first law of thermodynamics, that is delta Q is equal to delta U plus work done. So since work done is equal to P into delta V, so just put the value of work done in the expression of the first law of thermodynamics. We will get delta Q is equal to delta U plus P in P dV. All right. But we know Cp is equal to delta Q divided by delta T. Yes or no? So this expression comes from delta Q is equal to delta U plus P dV. So here just put the value of delta Q. So delta Q is this one, delta U plus P dV. So here put the value of delta U plus P dV, P delta V divided by delta T at constant pressure. All right. Specific heat capacity of water. So variation in the temperature range 0 degrees Celsius to 100 degrees Celsius. So the curve, uh, specific heat versus temperature, this one. This is not a linear curve. So here at 0 degrees Celsius, the specific heat capacity is approximately 1.008 calorie per gram per degree. Specific heat capacity decreases to its minimum value of about 0.998 calorie per gram per degree Celsius, around 35 degrees Celsius. All right. After that, uh, 35 degrees after 35 degrees Celsius, it gradually increases, reaching approximately 1.008 calorie per gram per degree Celsius at 100 degrees Celsius. All right. So average specific heat capacity of water across this temperature range is 1 calorie per gram degree Celsius, which is commonly used for calculation. Relationship between Cp and Cv for an ideal gas. So we will find out the here relationship between Cp and Cv using the first law of thermodynamics. So we know first law of thermodynamics, that is delta Q is equal to delta U plus delta W, and we specific heat at constant volume, that is Cv is equal to delta Q divided by delta T at constant volume. All right. So putting delta Q in Cv, the value of delta Q is equal to delta U plus delta W. So put the value uh, delta Q in Cv from equation first. Then you will be get Cv is equal to delta Q divided by delta T at constant volume is equal to delta U plus delta W divided by delta T. All right. So this expression comes from first law of thermodynamics. So specific heat at constant volume, expression becomes Cv is equal to delta U plus 0 divided by delta T. Here the work done is 0. Now here question arises why? Because this is the specific heat at constant volume. The volume is constant, so there is a no work done. So integration P dot PdV equal to 0 because work done depends on volume, change in volume. So Cv become delta U plus delta U divided by delta T. All right. Now specific heat at constant pressure. The mathematical expression is Cp is equal to delta Q divided by delta T. Now again here we will use the first law of thermodynamics, that is delta Q is equal to delta U plus PdV. So put the value of delta Q in the expression of Cp, you will be get Cp is equal to delta U divided by delta T plus P into delta V divided by delta T. Alright, this expression comes after the putting of delta Q in this relation. So now we will calculate the Cp further solving this expression. So Cp is equal to Cv plus P into delta V divided by delta T. Why Cv? Because we know Cv equal to delta U divided by delta T. So we here just replace the value of Cv, delta U divided by delta T. So it becomes Cp minus Cv is equal to P into delta V divided by delta T in at constant. Alright. Now we will solve RHS term using the ideal gas equation. So then the equation of state for 1 mole, it means the value of mu is equal to 1. So the ideal gas equation becomes PV is equal to RT. At constant pressure, the expression for ideal gas equation is become P into delta V is equal to R into delta T. So we integrate and differentiate it at constant pressure. So expression become this. So here further solving this expression, you will be get R is equal to P into delta V divided by delta T. All right. So putting this in equation, Cp minus Cv is equal to P into delta V divided by delta T. So you will be get Cp minus Cv is equal to R into delta T divided by delta T. So delta T cancel out. All right. So the remaining terms is Cp minus Cv is equal to R. And this is the Mears relation. This is very important term. Specific heat at constant pressure minus specific heat at constant volume is equal to R, where R is the universal gas. All right. Thermodynamic state variables. Basically, thermodynamic state variables are the measurable properties that define the state of a system in thermodynamics. Thermodynamic state variables are indeed classified into two main categories. First, intensive variables, and second, extensive variables. We will learn both one by one. So first, here, intensive variable. An intensive variable is a physical property of a system that does not depend on the amount of matter present. It means it is independent of matter. Example: temperature, pressure, and density. So these are the intensive variables. All right. These variables does not depend on amount of matter. All right. It is independent of amount of matter. If amount of matter increases, decreases, there will be no change in intensity. All right. Second is extensive variable. So extensive variable. An extensive variable is a physical property of a subsystem that depends on size or mass of the system. So we can say extensive variables depends on size or mass of the system. All right. Example: mass, volume, moles, internal energy, enthalpy, entropy, and Gibbs free energy. So these are the examples of extensive variables. In simple words, if we want to differentiate it, differentiation between the intensive variables and extensive variables. So we can say intensive variables depends on size or mass. No, intensive variables are independent of matter. Independent of matter. It does not depend on matter, like temperature, pressure. Whereas extensive variables depends on size or mass. So mass, volume, moles, internal energy are the extensive variables. I hope this is clear. Non-equilibrium states. Here, we will talk about some conditions of non-equilibrium state. So, thermodynamic system is not always in equilibrium. Example: suppose we have a gas particle, and that gas particles allowed to expand freely against vacuum is not in equilibrium state. Figure 11.6a. So here we have a, this one is gas particle. Particle partition in the box is suddenly removed, uh, leading to the free expansion of the gas. So when the particles suddenly removed, and we can say there is a happen free expansion, so we can say this is not an equilibrium state. During rapid expansion, pressure of the gas may or may not be uniform throughout. It means uh, when the partition is removed, there is a rapid expansion of the gas particle throughout the volume. So during expansion, we can say the pressure of the gas fluctuates. Some molecules have a higher pressure, some molecules have a lower pressure. So there is a n- uni there is a we uniformly they are not uniformly expanded. So we cannot define pressure during this rapid expansion process. It means that a system is in no system is not in equilibrium. Then we cannot define thermodynamic states variables for that system. So these type of systems are not stable equilibrium. All right, where Why? Because there is a rapid expansion, and during rapid expansion, the pressure may not be uniform throughout. Now, here question arises: if uh, the if during the rapid expansion, the pressure of the gas be uniform throughout, then uh, is it the equilibrium? Yes. Then the pressure of the gas may be uniform. So similarly, a mixture of gases like petrol, vapor, and air encounters a spark. So when these then when mixtures of petrol and air collides, so there is a spark, or we can say uh, explosive chemical reaction is going. So an explosive chemical reaction occurs, causing rapid combustion. All right, and the system becomes non-uniform. Why? Because of rapid combustion, and due to rapid combustion, the temperature and pressure is not uniform. If the temperature and pressure throughout the explosive chemical reaction is not uniform, so this indicating a not equilibrium state. So this is also a example of a non-equilibrium state where petrol and petrol vapor and air collide and encounters a spark. All right, equation of state, a mathematical relation connecting the state variables of a system. For mu moles of an ideal gas, equation of state is PV equal to mu RT, where uh, P is equal to pressure, V is equal to volume, T is equal to temperature, and mu is equal to number of moles of ideal gas. PV is equal to mu RT. This is a very important concept. If any three are known, if P, B, and mu and R are known, then fourth is determined. All right. Summary. Heat capacity is the amount of heat needed to raise the substance temperature by 1 unit. Specific heat capacity is heat required per unit mass to raise temperature by 1 unit degree Celsius or Kelvin. Molar heat capacity is heat required per mole to raise temperature by 1 unit. And specific heat at constant volume measures heat capacity when volume is fixed. From these lines, we can say heat capacity mainly two types. First, specific heat capacity. Second, molar heat capacity. All right. So if we talk about the specific heat capacity, this is also categorized in two parts: specific heat at constant volume, constant. All right. Specific heat at constant pressure, CP, measures heat capacity when pressure is fixed. Mears relation states that Cp minus Cv equal to R for ideally. Thermodynamic state variables come in two types: intensive variables and extensive variables. If we talk about the intensive variables, so it is independent of system size. If we talk about the extensive variables, dependent on system size. All right. Intensive variables uh, include temperature, pressure, and density, whereas extensive variables include mass, volume, internal energy, and entropy. State variables can only be defined for systems in equilibrium. equation of state PV is equal to mu RT relates pressure, volume, temperature, and moles for an ideal. Alright, state variables which depends on initial and final state. It is path independent variables like internal energy. For cyclic process, internal energy should be 0. Now we have some practice questions and this is homework for you. First, what is heat capacity of 2 kilo of water if 40 to 100 joules of heat energy increases its temperature by 0 0.5 degrees Celsius? Alright. So in this question, you have to find out the heat capacity. So the given formula is C is equal to Q divided by delta T. So using this formula, calculate the heat capacity. Second, using the first law of thermodynamics, that is delta E is equal to Q minus W. Here is the energy. Alright. So calculate the change in internal energy. It means delta E. Here you have to find out the delta E, change in internal energy. E and U both are same. We will use E and we use E and both. So calculate change in internal energy of a system that absorbs 800 joule of heat and does 300 joule of work. Alright. So just put the value of Q and value of W and subtract them. You will be get the delta E. If 1000 joule of heat is added to a metal block with a mass of 0.5 kg and its temperature increases by 10 degrees Celsius, what is its specific heat capacity? So in this question, you have to find out the specific heat capacity. Fourth, a gas expands and does 200 joule of work while absorbing 500 joule of heat. According to the first law of thermodynamics, what is the change in the gas internal energy? So in this question, you have to find out the change in internal energy of the gas molecule. All right. Calculate the amount of heat energy needed to raise the temperature of 3 kg of aluminium from 20 degrees Celsius to 35 degrees Celsius. All right. And specific heat capacity is given, that is 900 joule per kg degrees. Thank you for your attention. I hope all concepts are clear.